In this video, I'm going to look at second-order differential equations when the right-hand side is not equal to 0. There is a standard procedure for doing this. It takes a little while to explain it, but once you've got hold of it, it's really very simple. Firstly, let's just look at the general form of a second-order differential equation, linear with constant coefficients. Firstly, we proceed, as we have done in the previous videos, to find the general solution when f of x is 0. This is now called the complementary function and usually written as CF. So that is the first part. Find the solution as we've been doing in the past videos with fx equals 0. It is then called the complementary function. The complementary function contains two arbitrary constants. The next thing we do is to look for something called a particular integral, pi, which has no unknown constants. That's why it's called particular. It is a single function, no arbitrary constants. Guidance on that comes later. The general solution then of your differential equation is y equals the complementary function plus the particular integral. Justification for that I will do in a later video. Finding the particular integral. It doesn't actually matter which particular integral of very many we find. There are many possible particular integrals, and these rules that I'm going to give you will allow us to find a particular integral easily. Any particular integral will work. So if f of x is e to the kx, we try y equals lambda e to the kx. Sometimes there are complications. If e to the kx appears in the complementary function, then we need to try lambda x e to the kx. If x e to the kx appears in the complementary function, we need to try lambda x squared e to the kx. This will make more sense later. E to the kx must appear on its own in the CF. If you've got something like e to the kx sine mx in the complementary function, then you still try lambda e to the kx. So don't worry too much about what's written in blue. Mostly we're going to be looking happily at the red. What happens now if our function of x, our right-hand side, is trigonometric? If f of x is sine kx, or if f of x is cos kx, or if f of x is a combination of the two. In all three cases, you must try lambda sine kx plus mu cos kx. Don't think that if f of x is sine kx, you only have to try sine kx. If you've got sine kx, you must try both. Same sort of problem. If sine kx or cos kx both appear in the CF, then you multiply by x to get out of trouble. Again, don't worry too much about the blue. If f of x is a polynomial of degree n, then for the particular integral, you just try a polynomial of degree n. You must have all the terms. If f of x was x squared, you would need to try ax squared plus bx plus c. You would need to try all terms of your polynomial. Again, there is a complication. We can come back to that at a later date. In general, if you're trying to find a particular integral, you start off with something similar to the function of x that you have on the right-hand side of your equation. Well, let's move on to an example. The procedure is quite simple. We proceed as if the right-hand side was 0. We find the auxiliary equation. which is m squared plus 6m plus 5 equals 0. That gives us m plus 5, m plus 1 is 0, and therefore m is minus 5 or minus 1. Complementary function is what we did call the general solution beforehand. The complementary function is y equals a e to the minus 5x plus b e to the minus x. So that you should be familiar with. Now we have to look at what happens on the other side. Here we have a polynomial of degree 1. So for the particular integral, we are going to try a polynomial of degree 1. And so in this case, we're going to try y equals lambda x plus mu. Not just lambda x, it must be the most general polynomial of degree 1 that we can. In this case, dy by dx is equal to lambda, and d2y by dx squared is equal to 0. Substituting in the differential equation gives us that d2y by dx squared is 0, plus 6 dy by dx is 6 lambda, plus 5y is 5 times lambda x plus 5 mu. So that is substituting in the differential equation. The other side is 2x. Solving that, we get that lambda is equal to 2 over 5, and mu is equal to minus 12 over 25. And therefore, my particular integral is y equals lambda, which is 2 over 5x, minus 12 over 25, lambda x plus mu. The general solution of my differential equation, therefore, this is the sum of the complementary function, which is a e to the minus 5x plus b e to the minus x, the top of the screen, plus the particular integral, which is plus 2/5 of x minus 12 over 25. A very straightforward procedure, and once you've got used to it, you'll have no trouble doing it. For my second example, I'm going to look at d2y by dx squared minus 2dy by dx minus 3y is 3e to the 2x. These all start the same way. The first thing we do is to look for the auxiliary equation. That is m squared minus 2m minus 3 equals 0. If I factorize that, I get m minus 3, m plus 1 is 0. M is therefore 3 or minus 1. So my complementary function, which is the solution of the equation equals 0 that we're used to, my complementary function is y equals a e to the 3x plus b e to the minus x. Now, for the particular integral, we are going to try y equals. Well, let's just have a look at it. Our function up here is e to the 2x. We should be trying lambda e to the 2x, unless, and it doesn't, e to the 2x appears in the expression here, in the complementary function. So we can go ahead with the easy bit, just use lambda e to the 2x. We need to work out dy by dx. That's 2 lambda e to the 2x, and d2y by dx squared That is going to be 2 times 2. That's 4 lambda e to the 2x. Substituting in the differential equation, d2y by dx squared is 4 lambda e to the 2x, minus 2 dy by dx is 2 times 2 lambda, that's 4 lambda e to the 2x, minus 3y, that's 3 times lambda e to the 2x, and that equals 3e to the 2x. That's not difficult to solve. 4 lambda minus 4 lambda is 0. I have minus 3 lambda. E to the 2x equals 3e to the 2x. Therefore, lambda is minus 1. And therefore, my particular integral is y equals minus e to the 2x. My general solution, therefore, is the complementary function a e to the 3x plus b e to the minus x plus the particular integral minus e to the 2x. Very straightforward. The third example looks fairly similar to the one we've just done, but I'm afraid it has a bit of a difference. So let's find the auxiliary equation. M squared minus 6m plus 9 equals 0. That is m minus 3 squared equals 0, and therefore m equals 3 or 3 coincident roots. If we have coincident roots, the rule is that y is equal to ax plus b times e to the 3x. In this case, we have e to the 3x on the right-hand side. We have e to the 3x appearing in the complementary function. We also have x e to the 3x appearing in the complementary function. So in this case, we have to try, for the particular integral, we try y equals x squared lambda x squared e to the 3x. And this is because e to the 3x and x e to the 3x both appear in the complementary function. Okay, now we need to do some differentiating. We get dy by dx is differentiating the x squared. I get 2 lambda x e to the 3x plus differentiating the e to the 3x, 3 lambda x squared e to the 3x. Second derivative, d2y by dx squared. Differentiate the x, I get 2 lambda e to the 3x plus differentiate the e to the 3x, I get 6 lambda x e to the 3x. Going to the second term, differentiating the x squared gives me 3 lambda times 2x, that's 6 lambda x e to the 3x. And differentiating the e to the 3x gives me 9 lambda x squared e to the 3x. We have to substitute this in the original differential equation. d2y by dx squared is 2 lambda e to the 3x plus, and I'm going to combine the two next terms, 12 lambda x e to the 3x plus 9 lambda x squared e to the 3x. So that is d2y by dx squared minus 6 times dy by dx, 6 times 2 lambda x e to the 3x plus 3 lambda square x squared e to the 3x plus 9y plus 9 lambda x squared e to the 3x. And that equals the right-hand side, which is e to the 3x. If we look at this, we can see some nice things happening. We have 12 lambda x e to the 3x minus 12 lambda x e to the 3x. We have 9 lambda x squared e to the 3x minus 18 lambda x squared e to the 3x plus 9 lambda x squared e to the 3x. So the x squared e to the 3x goes, and we just have 2 lambda e to the 3x. Something nice will always happen when you get this type of equation. That's equal to e to the 3x, and therefore lambda is equal to a half, and our particular integral is y equals a half x squared e to the 3x. And the general solution, therefore, is y equals complementary function. It's just at the top of the page, ax plus b e to the 3x plus particular integral a half x squared e to the 3x. Fairly straightforward. Just have to do what we're told. For the last example, I've decided to take one which has cos 2t on the right-hand side. We start this in the usual way. The auxiliary equation is m squared minus 3m plus 2 equals 0. That gives us m minus 2, m minus 1 equals 0, and therefore m equals 1 or 2. Complementary function, which I expect you're beginning to get used to by now, y equals a e r. It's not y, I'm dealing with x and t in this equation. X equals a e to the t plus b e to the 2t. So that's easy, that's straightforward. Particular integral, we're going to try x equals, now this is where it's very easy. People just think they might try lambda cos 2t. Nope, you must try something with both cos 2t and sine 2t. Lambda cos 2t plus mu sine 2t. This gives me that dx by dt is going to be minus 2 lambda sine 2t plus 2 mu cos 2t, and d2x by dt squared is going to be minus 4 lambda cos 2t, and by the time I've differentiated the cosine, minus 4 mu sine 2t. Substituting in the differential equation gives us d2x by dt squared is minus 4 lambda cos 2t minus 4 mu sine 2t, minus 3 times dx by dt is minus 2 lambda sine 2t plus 2 mu cos 2t plus 2x plus 2 times lambda cos 2t plus mu sine 2t, all has to be equal to 4 cos 2t. Well, if we simplify that, we get that minus 2 lambda cos 2t minus 6 mu cos 2t minus 2 mu times sine 2t plus 6 lambda sine 2t is equal to 4 cos 2t. Well, if those are going to be the same expression, I should really write a triple equals or triple line equals. If those are going to be the same, then looking at sine 2t, I get minus 2 mu plus 6 lambda equals 0. That gives me that mu equals 3 lambda. And looking at cos 2t, I get minus 2 minus 6 lambda minus 6 mu is equal to 4. If I put mu equal to 3 lambda, I get minus 20 lambda equals 4. And that gives me that lambda is minus 1 over 5. Mu, which is 3 times lambda, is minus 3 over 5. And so the particular integral is x equals, lambda is minus a fifth, that's minus a fifth cos 2t. Mu is minus 3/5 sine 2t. And that gives us that the general solution is x equals complementary function, which is at the top of the page, a e to the t plus b e to the 2t plus the particular integral, which is minus 1 over 5 cos 2t minus 3 over 5 sine 2t. So those are 3 or 4 examples showing you how we find a particular integral. More about the justification of the method and so on in a later video.